up. Okay, it looks like we're live. Welcome to week 2. I'll put an agenda up for today. By the way, I feel like I should mention something that I mentioned this last week and it's kind of been eating at me. So I said that I don't have childcare, and that's not entirely true. What is the situation is that my partner and I have childcare outside of our home in the morning, and then in the afternoon we trade off taking care of our daughter. So my daughter is at home, but it's not as though I'm leaving her completely unsupervised during this time. In fact, my partner is taking care of her. But she might wander in at some point. So in fact, I kind of hope she does, because I want people to get to meet her. But hopefully it won't be an everyday occurrence. All right. So, on the agenda for today, we're going to recap of what happens before relation from last time. Today we're going to talk about partial orders and total orders. Lamport clocks, and vector clocks. I think that should be enough for today. All right, so last time we covered a lot. The happens before relationship is the particular thing that I would like to recap. So could somebody recap the definition of the happens before relation for me? You can either shout it out or type something into Zulip. When do you know that two events are related by happens before? Good, okay. So there's kind of 3 cases, right? So if you have 2 events that are in the same process, and A happens before B in that process, then you know A happens before B generally. The second case is if A is a send and B is the corresponding receive, then you know A happens before B. And the third case is what makes the relation transitive. So then, if you had, for instance, a message send that was event A, a receive, the corresponding receive, call that B, and C here. Actually, let's call this one C and this one B. Then you know A happens before B because these 2 events are related by happens before, and so are these. Or maybe it would look like this. Here again, A happens before B. So those are the pieces of the happens before relation, and you can put them together. So if you've got a bunch of events, you can use this definition to figure out what happened before what. Or at least you could if you had an efficient way to compute what's in the happens before relation. So we'll talk about that today. Before getting to that, let's just put up a bunch of events and remind ourselves how we can talk about events being related or not related. So if we had 3 machines, or 3 nodes, let's just put a whole bunch of events and messages here. Okay, so what are some of the relationships between events in this picture? Um, for example, if I were to pick out A and E, are those events related by the happens before relation? Sure, yeah, because we can follow this line here from A to B, and then E comes after B on the same process line. So we have A happens before E. What about D and A? No, those ones are not related. So if you look at A here, if you try to follow, what are all the places you can get from A? Well, you can get to B and you can get to E, but you can't follow this line backward. You could get to F and G. So we don't have that A happens before D, and then similarly for D, we can't get to A from D either. So it's not the case that A happens before D, nor is it the case that D happens before A. So instead, we would say that A and D are concurrent, and sometimes that's written like this. So in general, if you have a whole bunch of events, here, A, B, C, D, E, F, G, H, so you have this set of events, right? And you have this relation that relates some of the events to other events. But there's not necessarily going to be a relationship under the happens before relationship for every pair of events that you can pick out here. Mathematically speaking, what would you call the happens before relation? Does anyone know? Yeah, it's transitive for sure. It is transitive relation. But there's a name for this kind of relation. Good. Yeah, somebody just mentioned it's a partial order. So, does anybody here know what the definition of a partial order is? Well, let's go over it together. By the way, it's going to turn out that the happens before relation is actually not quite a partial order, according to the rules that I'm about to give you. So we'll see why in just a moment. So a partial order is actually two things glued together. So first, it's a set. Let's call it S. Together with a binary relation. Which is often written using something like this that looks like less than or equals, that lets you compare things from the set S. And has the following properties. Help me out here. What are the properties that the binary relation in a partial order is supposed to have? Anyone know? I'll give you the first one for free. Reflexivity. So that means for every element of S, let's call it A is related to itself. What else? What else is going to be true about the binary relation in a partial order? If you don't know, you can look it up on Wikipedia. Ah, somebody just said, okay, somebody said symmetry. Interesting. So symmetry would be a property of it if it was an equivalence relation, but it's not going to be an equivalence relation. Anti-symmetry, good. So what does anti-symmetry mean? Well, let's say that I have some A and B that are members of the set. And let's say that if I want to claim that if A is related to B by the relation, and B is related to A, what has to be true about A and B then? Yeah, that's right. Good. So A has to be equal to B. So if I'm going to go around saying that A is less than or equal to B and B is also less than or equal to A, well, the only way that can be true is if A and B are the same. So that's what anti-symmetry says. And the last part, transitivity, which we actually already talked about quite a bit in the context of happens before, but it's something that's actually true of every partial order. And transitivity just says that for all A, B, and C that happen to be elements of this set S, then if A is related to B and B is related to C, then A is related to C. So there are lots and lots and lots and lots of relations that are partial orders. It's a pretty ubiquitous notion that comes up all over the place in computer science. Happens before is just a particular one. Let's glance back at the definition of partial order here and just try to spot check to see whether it makes sense to say that happens before is a partial order. And I'll give you a spoiler, which is that it's actually not quite. Okay, so is the happens before relation a partial order? Well, first of all, we need to be talking about a set, right? So when we talk about happens before, what set are we talking about? That's right, yeah, we're talking about the set of events. So just like in this picture we just saw here, we have a set of events here. How many events? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 events here. So that we'll be talking about the set of events in a particular execution. So back to the definition of partial order. So in this case, the set just looks like this. Looks like a set to me. Okay, and the relation that relates those events, the happens before relation, is supposed to have all of these properties. Well, yeah, let's take the easy one first, right? Is the happens before relation transitive? That's right, yeah, absolutely it is. It's right there in the definition of happens before that we just looked at. So, check. We got that covered. What about anti-symmetry? Well, this says, okay, so for all A and B that are in the set, so pick out any two events from there, this says, if A is related to B and B is related to A, then A equals B. Well, so let's see. If you picked out two events from here, let's say like D and E, okay? If D happens before E and E happens before D, does that even make sense to talk about? Like, is there any situation in which one event happens before the other and also the opposite? Like going back to this picture here, does it make any sense to say that here, I mean, it's clear from looking at this that D happens before E, but does it ever make sense to say like one event happens before the other and then also the opposite? No, yeah, that's not possible. So what that means in terms of the definition of partial order for us is this is actually what we call vacuously true. So we have this anti-symmetry property for the happens before relation. Okay, so we have those two criteria. What about reflexivity? Given an event, any event here, let's say G, does it make sense to say G happens before G? It doesn't make sense to me. What would that even mean? If I were to say G happens before G or A happens before A. No, it's not clear what it would mean for an event to happen before itself. So this is not true. So this here, these check marks and X's here are particularly to do with the happens before relation. So we're checking to see whether happens before is actually a partial order according to these criteria. And it turns out that it's not, because it's not reflexive. So happens before is not quite a partial order. Rather, it's what's known as an irreflexive partial order. So when you're talking about an irreflexive partial order, it's sometimes also called a strict partial order, but I prefer to use the word irreflexive just to emphasize the fact that reflexivity is the property that we lose. So happens before is an irreflexive partial order, but you'll often hear people, including me, just saying it's a partial order. So I'm letting you know that it is in fact not quite a partial order according to the definition of partial order. It's fine to say partial order as long as people know what you mean. But I wanted to give the real definition of partial order here because it's such a ubiquitous concept and we're going to see it so often that it's useful to know. So why don't we talk about something that is in fact an example of a partial order, truly a partial order and not merely an irreflexive partial order. So a good example of that is set containment, or set inclusion, as it's sometimes called. So in this case, the set S would be the set of all subsets of a set. So let's say that the set that we're talking about is ABC, like that. So then S would be the set of all subsets of that. So we've got like the empty set, and then the set containing A, set containing B, set containing C, the set with A and B, A and C, B and C, and then the set containing all three. So that's our set, S. This set has 1, 2, 3, 4, 5, 6, 7, 8 elements, and we can order those by set inclusion. Which would look something like this. So at the bottom, you've got the empty set. One level up from that, you've got the sets containing A, B, and C. Above that, you have the two element sets. And then at the top, the set of all three. Classic example of a partial order. So why is it a partial order? Because those three properties are true, right? So reflexivity, anti-symmetry, and transitivity. So for example, if we were to just look at a particular element here of S, that element is a subset of itself. Not a strict subset, but it's a subset of itself. The same is true for anything else here. It's considered a subset of itself. So we have reflexivity. What about anti-symmetry? Somebody just asked in chat, how is a set of 3 letters a partial order? Well, so this here is the set that we're taking subsets of. So the partial order is on this set S, which is the set of all subsets of that. So this set S that has 8 elements here, that set can be ordered by set inclusion. And so what we're doing is we're defining this set inclusion order on the set S, which is the set of subsets of this set up here. So we just looked at this relationship, which was reflexivity. What about anti-symmetry? So anti-symmetry says that in this case it would be if something is a subset of something else and also the opposite, then they have to be equal. So in this case, for example, I can't come up with anything here where something is a subset of something else and also the opposite is true without them being the same. So, for example, the set containing A and B is a subset of the set containing A and B, and also the opposite of true. We'll notice that they're the same, and that would have to be true. Okay, somebody just asked in chat, so S is the partial order? Well, almost. So we just said, what is a partial order? It's 2 things glued together. So a partial order is a set together with a binary relation. So the partial order in this case is the combination of S and this binary relation on elements of S. So we could write it like a pair, like this. And then what about the last part of transitivity? Well, in this case, transitivity would be something like, well, the set containing A is a subset of the set containing A and B. The set containing A and B is a subset of the set containing A, B, and C. Therefore, we can put those two pieces together and get that the set containing A is a subset of the set containing A, B, and C. So we got all three. We have that this particular binary relation is reflexive, anti-symmetric, and transitive. So that means that we have a partial order. Now notice that not everything here is comparable, right? By the relation. So in other words, if I were to just take the set containing A and the set containing B, neither of those is a subset of the other. So you're going to have some elements in general in a partial order. You may have elements that are not comparable like this. So what does that have to do with us? Well, for us, when we're talking about our favorite relation, the happens before relation, elements that are not comparable are exactly the ones that the happens before relation says are concurrent. So if we go back to the picture that we were showing a second ago, of a whole bunch of events that happen in an execution of a distributed system. Like we said, some of these events are going to be concurrent, like A and D, for example. So those are events that aren't ordered by the partial order. A total order is different. If you have a total order, then every pair of events is ordered. But we don't have that here. Instead, we have a partial order. I'll bring back this picture for a second. So this is a real, genuine example of a partial order that has all the properties, reflexivity, anti-symmetry, and transitivity. And the happens before relationship is just a little different because it doesn't have that reflexivity property. So the happens before relationship is what we call an irreflexive partial order. But in every other way, it's a partial order. Questions about this? Okay, let's come back to our definition of the happens before relation. Here it is one more time. It's just a pictorial definition, but I think that's good enough for us. So if A and B are events in the same process and A comes before B on that process, then we have A happens before B. If A is a send and B is the receive that goes with it, then A happens before B. And then the transitivity part. So if A happens before C and C happens before B, then A happens before B. There were a couple of good questions just now in chat. So one person asked, what's the difference between a partial order and a partially ordered set? There's not really a difference. So a partial order, like we said, is a set together with a binary relation, right? So partially ordered set. Same thing. And sometimes people call it a poset for short, which just means partially ordered set. So same thing, it's a set together with a relation that lets you compare elements of that set. But as we saw, maybe not all the elements are comparable. And somebody else asked, could I reiterate the difference between a partial order and a total order? Well, going back to this picture of our example of a partial order, which was set containment that we just saw, notice that there are some elements of S here, like pick out these two elements, for example, the set containing A and the set containing B, that aren't comparable according to this, this binary relation. So we can't say that A is a subset of B, nor can we say that B is a subset of A. So that can happen in a partial order where some elements may not be comparable. On the other hand, if it's a total order, every element is going to be comparable. What's an example of a total order? Can somebody give me one? What's an example that's, what's the simplest example that you can think of something that's totally ordered? The alphabet, okay. A set containing one element, yeah. So the example that I was going to go with was the natural numbers, which somebody just mentioned. So if I were to try to order the natural numbers, if I were to draw a picture, they just go in a straight line, right? So there's not any situation where you have two numbers and it's like, oh, well, these are not comparable, right? It's always going to be the case that if you pick out two numbers from the set of natural numbers, you know, any n and m, either if they're different, right? Then either n is going to be less than m, or m is going to be less than n, right? That's always going to be true. It's a total order. So there's no ambiguity there. Or even if they're not distinct, right, then this is true. So that's different from a partial order where you may have some elements that are not comparable that way. And our favorite example of that is in a distributed execution where you have a bunch of events. You might not be able to say that one event happens before the other, nor can you say the reverse. So that's exactly the situation where events are concurrent. And so you don't have this total order of events in a distributed execution unless you do something more to try to impose it. Okay, so this leads into our next topic. So last time we talked about clocks, right? And in particular, we mentioned a couple of different kinds of physical clocks. So physical clocks encompassed time of day clocks and monotonic clocks. But we also talked about problems with using physical clocks. So what did we say that the alternative was to using physical clocks? Logical clocks, that's right. So, let us speak no more of physical clocks. So this is an entirely different notion of clock. They will not tell us anything about time of day, and they will not tell us anything about time elapsed. Instead, they will only tell us about the ordering of events. So we're going to be talking about a couple of different kinds of logical clocks. The simplest kind of logical clock that I'm aware of is called a Lamport clock. And a Lamport clock is just a way of assigning numbers to events in a distributed execution. So the notation that we'll use for this is if you have an event, let's say event A, then the Lamport clock of this event is going to be written LC of A, like this. So what is a Lamport clock? What do they mean? What do Lamport clocks tell you? Well, a Lamport clock is going to be some integer, actually a natural number, that's going to be assigned to an event. So a Lamport clock might be 3, for instance. So let's say that the Lamport clock of A is 3. What does that mean? What does that 3 tell you? Well, here's the rule. This is called the clock condition. If A happens before B, then the Lamport clock of A is less than the Lamport clock of B. So this is the happens before relation that we've been talking about, and this is Lamport clocks. So we say that Lamport clocks are consistent with causality. That means that if there's a causal relationship between A and B, that is, if A happened before B, that's what it means for us, then we know that the Lamport clock of A is going to be less than the Lamport clock of B. So let's put a whole bunch of events up and try to assign Lamport clocks to them. Let's stick with our 3 machines. So here's the algorithm for assigning Lamport clocks to events. First, every process has to keep a counter. Initialized to 0. Second, on every event on a process, that process is going to increment its counter by 1. Third step is, when you send a message, you need to include whatever your current counter is along with the message. What do you think step 4 is going to be? I'll give you a hint. It starts when receiving a message, what do you think happens then? Good, yeah. So presumably it's going to have something to do with that counter that got included with a message when it got sent, right? In step 3. If a process is going to be including a counter value along with the message it's sending, then presumably that has to get used somehow on the receiving end. So that's exactly what's going to happen. So the receiver is going to do the following. When receiving a message, a process sets its counter to the maximum of the local and the received counters plus 1. Let's work through all of these events up here using this algorithm. So every process has to keep a counter initialized to 0. I guess I won't call it X, I'll call it LC. Okay, what happens first? Well, M0 is sending a message here. That's an event, right? So what does M0 have to do? Right, so this is an event. So following step 2 here, this process has to increment its counter by 1, so its counter is going to become 1. And it's going to include that clock value along with the message. We get here to, and I'll just put 1 right here to say that that's the Lamport clock value of this event. We get here to machine 1. Machine 1 receives the message. What does it do? Well, its current Lamport clock value is 0. It's getting a message here with a Lamport clock value of 1. Which one's bigger? Well, 1 is bigger than 0, right? So it's going to compare the two. It's going to pick the one that's bigger. That's this max part down here. So we're taking the maximum of our local Lamport clock, which was 0, and the received one, which was 1. So the bigger one was 1, and then we're going to add 1 to that. So the Lamport clock value now becomes 2 for this event, and it's going to update its local clock to that. What happens here for this next event on M1? Somebody tell me. Yep, so process M1 or machine 1 is going to go to 3. This event gets a Lamport clock value of 3, and that gets sent along. So here, machine 2 gets the message. What does machine 2 do? Right. So it's going to compare its local Lamport clock value to the one that was just received, which was 3. 3 is bigger than 0, so 3 wins. And then we add 1. So this Lamport clock value of this event here is going to be 4. We're going to update this to 4. And we keep going from here. So this event is another event on M2. So we get to increment there. That gets sent along here. 5 gets here. Now we're comparing 5 to 1. 5 is bigger than 1. So 5 wins, and then we increment again. Great. We've just assigned Lamport clock values to all of the events in our system. So we have this way of now assigning numbers to events. And we know that if A happens before B, then the Lamport clock of A is less than the Lamport clock of B. In other words, Lamport clocks are consistent with causality. So let's take a quick look at this and let's see if we think that's true. So, well, this event here we know happened before this one, right? Because they're on the same process line. And indeed, 1 is less than 6. Likewise, this event here happened before this one, right? Because this one is a send and this is the corresponding receive. And indeed, when we look at the Lamport clocks, we see that 3 is less than 4. So if you look at any pair of events here, you'll see that if A happened before B, then the Lamport clock of A will be less than the Lamport clock of B. So it checks out, and it's what we want. It's consistent with causality. By the way, in some formulations of this algorithm, you'll see it done differently. So sometimes message receives do not get counted as events. So here we chose to count message receives as events, but if you weren't counting message receives as events, then you could do that, and then the algorithm would be the same, except that you wouldn't have to do this +1 here. So if you've ever seen something like this before and it didn't have the +1, then that might be why. But today we're going to go with this notion of counting message receives as events, and so this is what the Lamport clock algorithm would look like. Okay, so we have this nice property, right, that if A happens before B, then the Lamport clock of A is less than the Lamport clock of B. What about the other way around? If the Lamport clock of A is less than the Lamport clock of B, do we know that A happens before B in general? We actually don't. So it's a little bit of a trick question because in this picture, it happens to be the case that whenever we have a Lamport clock that's less than another Lamport clock, like say 4 and 6, for example, 4 is less than 6, and it happens to be the case in this particular picture that for all the pairs where that's the case, we can also look back and say the one with Lamport clock of 4 happened before the one with Lamport clock of 6, and so on. But perhaps surprisingly, it turns out that this is not the case in general. So here's an example. So let's say again that we have 3 machines. And we'll do another Lamport diagram. Let's do it like this. Okay, so let's walk through the steps of the Lamport clock algorithm again, and let's try to assign Lamport clocks to all of the events here. So in case you still need it, here's the Lamport clock algorithm. I'll put it like that. Hopefully you can see most of this picture here. So above this is just the names of the 3 processes like that. So nothing's really being hidden from you here. Okay, so we want everybody to keep a counter, right, that's initialized to 0. So let's start out. Let's just start trying to assign Lamport clocks to these events. So this one here on M1 is the first event happening on this process. So it should get an increment. So that becomes 1. Lamport clock of this event is 1, and then that gets sent along. What happens over here? This is M2. Well, we're going to compare 0 with 1. 1 is winning. And then we add 1 to that. So the Lamport clock value of this event is 2. What happens next here on M2? Whoops, I forgot to update this here. Yep, so this event's Lamport clock value is 3. 3 gets sent along with the message all the way over to M0. M0 is going to compare the 3 with 0. 3 is going to win because it's bigger. So then the Lamport clock value, oops, but we forgot something because there was an internal event up here. So internal events count too. So this is also going to get a Lamport, or actually, let me ask you, what's going to be the Lamport clock value of this event up here? This is the very first event on process M0. Happens to be an internal event, but it doesn't really matter. So what's the Lamport clock value of that event going to be? 1, good. So that's going to be the Lamport clock value there. Now we get to this event here. I'll try to fit this all in view. So what's going to happen when machine 0 receives this message with a Lamport clock value of 3 and it compares to its own Lamport clock? Right, so 3 is bigger than 1. So the Lamport clock of that event will be 4. Here's another internal event, so that one gets 5. Coming back over here to machine 2, what's going to be the Lamport clock value of this event right here? I think I'll move the rules out of the way because I think we all pretty much know what they are now. So what's going to be the Lamport clock value of this one? That one's going to be 4, good. 4 is going to get sent along. We'll come here. Machine 1, whoops, I forgot to update these over here. Machine 1 had a Lamport clock value of 1 before. That's going to get compared with 4. Out of 1 and 4, 4 wins. And then we add 1 to that, so that's going to have 5. Here's the next event on M1. That one's going to be 6. And finally, 6 gets sent along here. And our very last one, we have 6 here, we have 5 here. 6 and 5 get compared, and 6 is bigger than 5, so 6 wins, and then we add 1 to that. Okay, so we've assigned Lamport clock values to all of the events in this execution according to the algorithm that we just gave. So let me draw your attention to a particular pair of events here. Let's look at this one here, A. Let's call it A. And let's look at this one here, which I'll call B. So the Lamport clock of A here is 1. And the Lamport clock of B is 5. But did A happen before B? So here's a trick for knowing whether one event on a Lamport diagram happened before another one. On a Lamport diagram, if you can reach B from A, then you know A happened before B. So if I can follow lines from A to get to B, then I know that A happened before B. But that's not the case here, right? If I were to start at A and follow arrows, I cannot get to B. I could start here and get to B, or here, or here. But I can't get there from here, right? So in this picture, you cannot reach event B from event A. So you cannot say that A happened before B, even though its Lamport clock is bigger. So, even though we have this thing that says that if A happened before B, then the Lamport clock of A is less than the Lamport clock of B, it's not the case that if the Lamport clock of A is less than the Lamport clock of B, then A happens before B. So somebody asked a question a little while ago on Zulip about really what we mean by causality. Like when I say A arrow B, like this, somebody asked, does this mean A caused B? Or does it just mean A happened before B, or what? Well, good question. What it means is that A potentially caused B. So it didn't necessarily cause it, but we say potentially caused. We can certainly say happened before. Whether it actually caused this event, whether it actually caused B, is another question. But you know that it could have been a cause, so that's why we say potential causality. Thanks for asking that one. So I think part of the reason you were asking that is because a little while ago, when I wrote this down, I wrote, the Lamport clocks are consistent with causality. So if I wanted to be really pedantic about it, I could say Lamport clocks are consistent with potential causality. So, because of what I just showed, coming back to this picture, where we assigned Lamport clocks to all these events, but we found that even though this Lamport clock of this event here is bigger than this one, that doesn't mean that this one happened before this one. So we say that although Lamport clocks are what we call consistent with causality, or consistent with potential causality, we say that Lamport clocks do not characterize causality. So, mathematically speaking, consistent with causality or potential causality, if you want to be precise about it, means if A happens before B, then the logical clock of A is less than the logical clock of B. That's what it would mean to be consistent with causality. And Lamport clocks have this property. Yay. But another desirable property is what we call characterizes causality. And that means that if the logical clock of A is less than the logical clock of B, then A happens before B. And Lamport clocks do not have this property. Sad face. So it's a little bit of a bummer, right? Lamport clocks are pretty convenient in the sense that it's pretty easy to run those steps of that algorithm that I gave a minute ago. It's pretty easy to assign Lamport clocks to events. So it sure would be nice if we had both ways of this relation here. It would be really nice if Lamport clocks were both consistent with causality and if they characterize causality. But sadly, that's not true. So what good are they then? Somebody just asked this great question in Zulub. What's the point of Lamport clocks? So what could we still use them for? Well, why would you ever want to use them? Well, we do know this, right? We have that if A happens before B, then the logical clock of A is less than the logical clock of B. So this is a logical implication. What's something that you can do with an implication? Anytime you have a logical implication, what's something you can do with it? No, I mean, like, some people are laughing at this question about, so what's the point of Lamport clocks? But it's a damn good question, right? What is the point? Well, here's what you can do with an implication. Anytime you have an implication, like P implies Q, like this, you can take what's called its contrapositive. So if P implies Q, in this case that means that not Q implies not P. So this notation here means not, for those unfamiliar. So that's kind of nice. So that's something that you can do. So coming back to Lamport clocks, well, the implication that we had was this, right? We had A happens before B implies that the Lamport clock of A is less than the Lamport clock of B. Well, if we plug that in here, then we have, this is P and this is Q, right? So here's our Q, here's our P. So then if it's not the case that the Lamport clock of A is less than the Lamport clock of B, then it's not the case that A happens before B. And this is still pretty useful information. So if it's not the case that the Lamport clock of A is less than the Lamport clock of B, then we can rule out the possibility that A happens before B. Now, that doesn't tell us everything we might want to know, right? We still don't know exactly what the relationship is here. So it might be the case that, B happens before A, or it might be the case that A and B are concurrent. We don't know which it is. But that's still pretty nice to know. It's nice to know that it couldn't possibly be the case that A happens before B in this situation if we use the contrapositive. So that's what Lamport clocks can be used for. They can rule out things as not having caused other things. It's still not everything that you might want to know, but it's nice. And it's fairly easy to compute. So if you look at what we did in this figure here, when we were assigning Lamport clocks to all these events, this is a pretty low overhead algorithm, right? All the additional information that we had to tack on to these messages as they were getting sent around here was one number. So that's really nice, right? If you only have to tack on one number, then that's not too much overhead. And it may not tell you everything that you want to know, but in distributed systems, everything is a trade-off, right? If you wanted to know more, you would need to pass around more information. And that would cause you to use up more bandwidth, and it might not be worth it, honestly. So Lamport clocks are pretty nice because they're a low overhead way to get some information about the ordering of events. And that's nice. So that's what Lamport clocks are for. They were invented by Leslie Lamport, who I mentioned on day one of class is the father of distributed systems, in a paper that was published in 1978. And you can go look it up yourself if you want. Look up Lamport 1978. The paper is called Time Clocks and the Ordering of Events in a Distributed System. So this paper is, parts of this paper remain deeply relevant today. Other parts of it are not so relevant, but it's considered one of the highlights of the distributed systems literature of all time. So it's a fun one to look at if you're interested in some historical perspective. All right, so I goofed and I didn't set up a quiz for today. My excuse is that I just got my first vaccine shot yesterday, and so my arm really hurts, and I'm not thinking straight. So I failed to set up a quiz for today, but I still think that you deserve your 10-minute break. So we're going to take our 10-minute break, and when we come back from our break, we will talk about a different kind of logical clock that, in fact, not only is consistent with causality, but also characterizes causality, unlike Lamport clocks. So let's do our 10-minute break starting now. I'll set a timer, and when we come back, we'll talk about a different kind of logical clock. See you in 10 minutes. Yeah. Okay, fine. A equals B, A is B, A, yeah. That's true. I did not define equality. Sure, yeah. Hmm. Yeah, in fact, the LSD seminar was attended by a few students from our class last week. So hopefully we'll get even more this next time. I think you were. Yep. Let me take a look. Yeah, so Patrick, the only change I would make would be to say for partial order, the binary relation may only be defined for some pairs. So a total order is also a partial order. It's just the special case of partial order where, in fact, you have the relation defined for every pair. So every total order is also a partial order. but not every partial order is a total order. Does that make sense? Right. I think so. All right, we're going to start again in a minute. All right, 1 minute is up. Hope everybody got a chance to get their eyes away from the screen. I really do mean it when I tell people to get eyes away from the screen. It's not enough of a break for your eyes to just look at something else on the screen. You should really look away from the screen. Otherwise, it's just more stress for your eyes. All right, so we just got done talking about Lamport clocks, and we said that the relationship between Lamport clocks and the happens before relation is this. In other words, Lamport clocks are consistent with causality. And the other direction that characterizes causality direction, the direction that would go like this, is not true. So it sure would be nice if we had some kind of logical clock that did exactly characterize causality, that did characterize the happens before relationship. Happily, it exists, and it gets used all the time in distributed systems. It's called a vector clock. So here's the property that's true of vector clocks. Or, if A happens before B, then the vector clock of A is less than the vector clock of B. And also, if the vector clock of A is less than the vector clock of B, then A happens before B. So that's if and only if this time. We have both directions of this implication. Not just if, like we had before, but if and only if. This is big. This means that vector clocks are consistent with causality and characterize causality. Okay, so how do they work? What's the definition of a vector clock? Well, remember a Lamport clock is just an integer, right, that's associated with an event. So, given the name vector clocks, what do you suppose a vector clock is? clock using vectors. Okay, that's one answer. Well, if a Lamport clock is just one integer, a vector clock is going to be a vector of integers. So this is the way that it works. First of all, we're going to say that every process keeps a vector. Of integers initialized to 0. How many do you think? How big is this vector going to be? Good. Yeah, the suggestion was as many entries as we have processes. That's exactly right. So there's going to be one entry in this vector for every process. Good. So if you had 3 processes, then every process's vector clock would start out like this, 0, 0, 0, initially. Okay. So just like with Lamport clocks that we just saw, we're going to use vector clocks to count events, but they're going to be more informative than Lamport clocks. So next part of the definition. On every event, process increments its own position in its vector clock. I wrote integers here, but they could really just be natural numbers. They're never going to go negative. By the way, when I say on every event, this includes internal events as well as sends and receives. So all events, sends, receives, and internal events. Next up, when sending a message, a process includes its current vector clock. So just like we saw with Lamport clocks a little while ago, with Lamport clocks, when you send a message, you're going to attach the Lamport clock to it. Same with vector clocks. When you send a message, you're going to attach this extra thing to the message, which is your current vector clock. And this is going to happen after the increment that happened in step 2. Because a send is an event. Okay, that covers sending. What about receiving? This is the most interesting part. Anybody have a guess at what happens with vector clocks when we receive a message? Indexing to the vector, well, that's certainly going to be involved. That's right, so you're getting a message, and it's got a vector clock attached to it, right? You've got to do something with that vector clock that you're receiving, right? And somehow it's probably going to involve comparing that to whatever vector clock you have yourself. So what will we do? Well, when receiving a message, process will update to the maximum of the local vector clock and the received vector clock. So this is its own. And this is the VC that was on the message. And it's also going to increment its own position in its vector clock according to step 2, because receiving is also an event. So this is all going to happen just like here. We're going to say because receives are events. So that's the vector clock algorithm. Somebody just asked a question, so they said, wait, but on the Lamport diagram, don't we end up with a vector at the end as well? So I think they were talking about with Lamport clocks. So this is a little different. With Lamport clocks, every event is going to get associated with just a single number. So if you wanted to, right, you could think of the Lamport clock of every process, right, and put them together and think of that being a vector. But this is going to be a little different. In this case, instead of just keeping one number, every process is going to keep a vector. And every event is going to get associated with a vector. So there was just a question, is step 4 element-wise? Right, so we're doing this max operation here on vectors, but we haven't defined what it means to take the maximum of vectors. So let's do that now. So if somebody just correctly anticipated in chat, it's going to be pointwise maximum. So for instance, if I have 2 vectors and they're, let's say, 1, 12, and 4, and say 7, 0, and 2, then what's the maximum of those 2 going to be? Good, yeah. So it's going to be what's called pointwise maximum or element-wise maximum. Okay, good. So coming back to this vector clocks algorithm here, we only have 3 more minutes for today, so we're going to have to save an example run of this algorithm for next time. But let's talk a little bit just about what this means. So we said that with Lamport clocks, we're using them to count events that happen, right? But we get more information out of vector clocks than we do out of Lamport clocks. So for example, if the Lamport clock of an event is just, say, the number 5, then all that tells you is 5 events have occurred, including this event that has the clock value of 5. That's all it tells you. 5 events have occurred. It doesn't say anything about where those events might have occurred. It just says that 5 events have occurred. But if you had a vector clock, for example, like if you had 5, 0, 0, so let's say that these are entries in this vector clock are each representing Alice, Bob, and Carol. This vector clock of 5, 0, 0 describes a world in which Alice has seen 5 events and Bob and Carol haven't seen any. Or another way to put that is it's a world where we know about 5 events that have happened on Alice and we don't know about any events that have happened for Bob and Carol. So this gives us more information than just the plain old number 5. And it turns out that this additional information is going to be exactly what we need to know to get that characterization of causality that we wanted to have out of logical clocks. So sadly, we're almost out of time, and we're going to have to save an example run of this vector clocks algorithm for next time. And next time, we're also going to talk more about how you compare vector clocks, which is kind of related to what I just said about the max operation. But that will have to be saved for next time. In the meantime, I know that you're hard at work on assignment 1. Some people have already started forming their teams for assignment 2 and beyond. Remember that you need to do that by Friday. And if you have questions about assignment 1, please, please, please ask them on Zulip. Also, be sure to go to section. So I know a lot of people got a lot out of going to Patrick's section yesterday, and Abhay has his section tomorrow. So that's a great place to go if you have questions about the homework. Otherwise, keep asking questions on Zulip, talk to us if you need help, and remember to get your team together. All right, I will see you on Thursday. Take care.